All right, so you can hear me clearly. Is there or is there any noise in the background, or it's clear?
It's clear. Your voice is clear.
Okay, perfect. So I'll share the screen and let's start. All right, so you can see the screen. Is it clear?
Yes.
Perfect. So we were discussing micrometers and Vernier calipers last time, and I think that's where the call dropped as well. So we'll start with the micrometer. It's very simple. Uh, let's just quickly revise. You have any object that you have to measure, you put it in this gap, and then you turn the thimble so you can lock the object between the spindle and the anvil, right? Between the jaws, or you can just call them jaws. Once you do that, you read this value, which is the highest scale division that you can see, which is at this point, it is this one. You can see my pointer. Large. Okay, so it's this one, right? So you read the immediate left division from this thimble, which is at this point, if you see it, this is 5, it is 5.5. So you note that down. So let's note it down over here, 5.5. This reading comes from the main or fixed scale. Fixed scale, right? The next step is to read the reading from this thimble, which is rotational. So you have basically fixed your object in here and locked it. So whatever reading that you have from this thing now, you'll see that it should come on this line, right? So anything, the value that falls on this line would be your reading. Now, the thing about this thimble is that it's really divided into 50 divisions. There are 50 divisions on this thimble, and once you turn this thimble, one division closes or opens. At that point, these jaws, the distance between the jaws by one division is 0.50 millimeters divided by the total number of divisions on this thimble, which is 50 divisions, right? So this gives you 0.01 millimeters. Now, this is a number that you have to multiply every time you note down a reading from the thimble. So in this case, we see that there is 25 over here, 30 over here, then you have 31, and this one is 32. So the reading that we will take from here is 32 multiplied by 0.01, which is 0.32. Note that all of these readings are in millimeters. And once you get the reading, this reading is from the thimble, you get these readings, all you have to do is just add the readings from fixed scale and the reading from the thimble. So from fixed, you have 5.5 millimeters, and from the thimble, you have 0.32 millimeters. Once you add that, you get 5.82 millimeters, right? And so
Does it
that's how
always have
you
50 divisions?
for a micrometer, yeah.
Yeah. Okay.
Okay, yeah. So this is what we get, right? Now, so any thing, you can put anything in between these two things, and you'll just rotate the thimble. It locks at one particular point. You'll note the reading on the fixed scale, note the reading on the thimble, which is basically a rotational barrel, and do the math, and you get whatever reading you get. So is it clear how do you take readings from a micrometer? So the procedure will be the same every time, right? So is that clear? You have to remember that how do you take the reading from main scale and the fixed scale? That's the only important part, right? So is that understandable?
Yes.
Right. Is it clear for everyone? Okay, I'll assume so. Right. So now we can move on to the Vernier caliper. And again, Vernier caliper is quite easy. You place any
Sir,
object.
someone wrote something in chat.
Okay, just thank you for letting me know. Can you repeat that? The micrometer one? Okay, so I'll just quickly repeat what we did for the micrometer. Whatever object that you want to measure, and it's relatively small, right? Its length is, or the size is comparable to millimeters. You place it in between this screw type thing, and this is called an anvil. So you put it over here, you start rotating this. Let me use a highlighter. You start rotating this thing, right? This thing is rotatable. So you'll rotate and it will move either this direction, or you can rotate it in the other way. So it will move towards this direction. So once you rotate it and the object that is in there is locked completely, once it's locked, then what you do is you read off the fixed scale, the value. So we have 0, 1, 2, 3, 4, 5, and the middle divisions are just half of those values. So at this point, you see it right next to this, the edge of this thimble, you see that there is this division, which is 5.5. So that's why I wrote the reading from the fixed scale as 5.5 millimeters. The next step is to read off a thimble. Now, for thimble, basically there are 50 divisions on thimble, and once you turn it through, one division will close, right? Or you can rotate it the other way and the division opens, right? So that means that the distance that this moves is 0.5 millimeters, because every division is like that, and you can divide that by 50, which is the total number of divisions. And so for each division you get it's 0.01 millimeters. And then what you do is, whatever reading that you take off from this micrometer, for example in this case, you read off whatever value matches with this straight line, and you see that this is 30, this is 31, this is 32. So 32, and you multiply that with 0.01, which is the least count for the micrometer, and you get 0.32 millimeters. Next step is just to add this value to this value, which is fixed scale value to the thimble value, and you get 5.82 millimeters. So is that clear, Rahil? All right, so I'll assume, okay, it's clear, perfect. Okay, so next is the Vernier caliper, and to read a Vernier caliper, all you have to do is whatever you have inside this, again, you move this movable scale. It's movable, as you can see over here. It can move in one dimension, so either to the right or left. You put the object that you want to measure in between these two jaws, and you start reading the scale. So you have this fixed scale and you have this moving scale. So you'll see, you'll read the highest scale division before this 0. So this is the 0 on the movable scale, and the highest scale division before that is what you will write down. Okay, so from your fixed scale, you'll take a value. And so if you see, this is 0, 1, 2, 3, 4, 5, 6, and this is 7, right? So you'll note down 7 millimeters from this fixed scale. Next step is you have to, so I'll just get rid of these lines. You have to read off this Vernier scale, or it's also called the movable scale. How do you read off this is you have to see where the divisions on the fixed scale and the Vernier scale match with each other, or they coincide with each other. So you see at this point, this is 0. It does not match with the division on the fixed scale. Even if you look at this one, it does not match with the division that is above over here on the fixed scale. Similarly, you can see neither does this match. This does not also match. There's a slight, it's a bit slided to the left. This one, if you draw a straight line through this one, you can see that it matches exactly with each other. So this is the value that you will note down. So we have to read this value from the Vernier scale. So that's this is 0, 0.1, 0.2, 0.3, 0.4. So from the Vernier scale, we get 0.4 millimeters. And again, to get a reading for the size of the object, you just add fixed
Sir,
to
can you
Vernier.
repeat the Vernier score? Vernier scale?
The Vernier scale, yeah, okay, I'll repeat it. So basically, anything that you want to measure, you will put inside the jaws, between the jaws of the scale. You'll look at the fixed scale. You will read the value. You'll read the value from the fixed scale, keeping in mind that the Vernier scale, wherever the Vernier scale's 0 lies, you will look at that, and the division that is to the immediate left on the fixed scale is what you will take. So you see, this is the 0 on the Vernier scale, and the division to the extreme left of this is this one. So we'll see what is this division. So this here we have 0, 1, 2, 3, 4, 5, 6, and 7. So this one is 7. So you'll note that down. Next is you have to read off a Vernier scale. How do you read off a Vernier scale? You will just see the divisions on your fixed scale, which is this one, and the divisions on your Vernier scale. They should match with each other. They should coincide with each other. So at this point, you see this is 0. It does not coincide with any division on the fixed scale. It lies in between this one and this one. So what about this one? If you look at this one, it is like this. And if I extend it in this direction, it still does not match with this division, right? It's not matching. So this is not it. Similarly, you can see even this one, it does not exactly coincide. So this is slightly to the left on the fixed scale, and on the Vernier scale, it's slightly to the right. But if you look at this one, this and this, so they match exactly with each other. So you will pick this reading and you will write it in front of your Vernier reading, right? So that would be your Vernier reading. So we'll read it in this way, that this is basically on a Vernier scale, this is 0, this is 0.1, this is 0.2, 0.3, 0.4, and this is 0.5. So we'll take 0.4 and we'll write it over here, and then just add the two values and you get the size of whatever object that you wanted to measure.
So for the fixed
So-
scale reading, the number has to be closer to 0?
You mean the reading that we take from this fixed scale, right?
Yes.
The number that is right before the 0 on the Vernier scale. So so the number that is right before 0 on the Vernier scale, the 0 is on the Vernier scale, but the number that you want to note is on the fixed scale, right? So that is 7 in this case. Okay, so that's clear?
Yes.
All right, perfect. So that's how you basically read off a Vernier scale. And then let's go back to this point. And so there's just this example of a micrometer as well. Let's read this one very quickly. A micrometer has zero error as shown in figure. Okay, so they're just telling you that there is a zero error in this micrometer. How can you tell? Well, you can tell because the thimble is not, the zero is not coming at this point, right? So it's at this moment, it's at this 0.05 millimeters. So you can say that if you're not measuring anything at this point, there is some zero error in this micrometer. It's a mechanical error basically. So, and the same instrument is used to measure an object with a reading as shown in this figure. So there is a zero error in the instrument. We know that, but we still decided to use this and measure an object's length or size. And we can do that if we know how to eliminate zero error. And we, of course, we know how to eliminate zero error. We just have to see what is the zero error in this length. So what is the zero error? Can anyone tell me at this, in this micrometer on this left figure, what would be the zero error?
0.005.
0.
005.
It would be 0.05. 0.
Okay.
Right. So 0.05 what millimeters, right? So everyone understands that. Why is the zero error 0.05 millimeters?
I didn't get that. Could you explain
Okay,
that?
so all right. So basically, we just this is the line, right? This is that line that we talked about. So we see that at this point on this thimble, we don't see this line does not coincide with a zero. And at this moment in this figure 1.1, there is nothing that is being measured. So it's closed. It's closed entirely with nothing in between, right? So if it's closed entirely with nothing in between, this should have read 0 at this point and 0 at this point, but it's not reading 0, which means that there is some mechanical fault in your micrometer, which is causing this 0 error. But we still can use this micrometer to make measurements as long as we can eliminate this 0 error. So the reason that it's 0.05 is because you see that this line comes and matches with this number 5 over here, but we know that every this thing is 0.01, right? So 0.01, and you multiply this with 5, so you get 0.05 millimeters. Right? This is because there are 50 divisions, and then you just divide every division, which is separated by 0.05 millimeters. You divide that by 50 and you get 0.01. So that's why we multiplied it with 0.01. So is it clear now, or?
Yes,
Yes, it's
100%
clear.
clear.
Okay. So that's the zero error. So we have zero error with us. Now we have to see, this figure shows the reading that the micrometer took, right? So it's not the actual reading. And the reason for that is because there is a zero error in the instrument. So this, if you have an error initially, then whatever reading that you take is the apparent reading, right? Now, apparent, the name suggests it all, that it's the reading that you can, it appears as though this is what the reading or the measurement is, but because there is a zero error, I'll have to eliminate that zero error from this reading. So what would be the reading over here? The apparent reading. Can you guess, anyone? How do I do it? So first I'll find the fixed scale reading, right? So what is the fixed scale reading on this thing? Here I have 0, this is 5. So 1, 2, 3, 4, 5. And then this is, yes, sorry.
7, I think 7.
This would be 7, and the immediate left is this one. So this would be
7.5.
7.5, right? So it would be 7.5 millimeters. So is that clear for everyone?
Yes.
Yes.
Okay.
Clear.
Okay, perfect. So that's 7.5 millimeters, and the reading on this thimble would be the one that matches exactly with this line, and that's
39.
39, right? So we'll just multiply that with so let me write this one over here first. So that's 7.5 millimeters, and from the thimble we get 39 into 0.01 millimeters. So that's 0.39 millimeters. So let's bring this thing over here. And so now all you have to do is add the two, right? And you get 7.5 plus 3 is 8, and you have 7.89, right? So that's your apparent reading. Remember that. So of course you have an option 7.89 over here, but you will not select that, because remember that you still have to eliminate this zero error. You have to get rid of it. So you're getting rid of an error, right? So that just means that whatever length that I found, I have to get rid of the zero error from this. So I'll just, how do we get rid of things? We subtract them,
Yes.
right?
Subtract.
So 0.05, and all of them have the units of millimeters. So that's what we have. And so this would be 7.8, sorry, 7. Yeah, it would be 7.84. 7.84 millimeters, right? So that's the actual length of your object, and that's option A. So is there any question? Anyone has any question, did not understand any part? Even if that thing was something that we did in the very beginning, I still have no problem in going through that. If anyone has any question.
No.
Okay, so it's clear. Perfect. Perfect.
Clear.
So now we'll move to the next topic of a simple pendulum. It's also a measurement device. You can say this is used really to find time period or to measure time really. Let's see, how does this work? Okay, so it's attached to, you can say it's attached to a ceiling, right? And the ceiling, it has to be rigid, right? So it's fixed and the ceiling is not going to move. You attach a string to the ceiling. So initially it looks like this. Let me draw it over here. So initially you attach a string. The string is very tiny, or you can say it's very, its size is so small that it's almost massless. And then you attach some bob. We call it a bob, or you just call it a ball really, right? So you attach a ball to this string. Now what you do is, just picture the situation in your head. You hold this and you move it over here. Now before you did that, this was in this position, right? If I did not hold the ball, if it's just hanging like that, it's at its resting position, and this position was called mean position. Mean position. So it's just without anything, only the only force that is acting on this is what, by the way?
Gravity.
Or the forces. Yeah, so gravity is, exactly. So there is weight of this, which is the gravity, and there would be some, remember Newton's third law. According to Newton's third law, what is the other force that could be acting on this ball? There would be some normal force, which really is in the form of the tension in the string, right? So there would be some tension built up in the string as well. So this is just remembering Newton's third law, which we'll talk about in detail. in the next topic, in specifically in dynamics, really, which is concerned with forces and all. But Newton's third law states that in very, very simple and rough language, that every action has an equal but opposite reaction. So this tension had to be there, right? So if there was this force mg, then there had to be some other force balancing that mg. Okay, so anyways, this is the mean position, right? Now, now let's say after some time you decide to move this like this, right? Sorry, this was the ball. Now you move it to this position, right? And let's just draw this normal line. So before it was at this position, this line is drawn to denote that this was the mean position, right? Mean position is just a resting position from which like the only force that is acting is force of gravity and the tension in the string, and it's just resting. You did not move it, you did not do anything to it. It's alone and it's resting like in its position, in a position, and that position is called the mean position. After some time you decide that let's just play with this thing, and you move it to the right, and then you can release it from that point, right? So it doesn't, so basically you can raise it to any height that you want. Of course, the maximum height that you can raise it to is the height of this ceiling, right? So you could have taken it to almost like this height and then released it from there. So, but anyways, whatever height that you are about to release the ball from is known as the extreme position. Extreme position. So whatever height that I raise this ball to, and I'm about to drop it or release it, that position of the ball is called the mean, the extreme position. So is this idea of mean and extreme position clear?
Yes.
Yes.
All right, great. So when you release it, what will happen? It starts to go in this direction, and then it will raise to some height in this direction, and then it will come back to its position, and then it will keep doing that. So that is basically called oscillation, right? Now, one oscillation is that, let's say that this is some point A, or let's call it P. Now, you raise it to this height. Let's just, actually, they have been following this PQR over here in this diagram. I have taken it like this. So let's just call it R, just staying consistent with the diagram. So let's just call it R. You raise it to this height, and then you release it from this point. It will come to this position, and then it will move, and it will go to this position. And then when it reaches this position, it cannot raise any higher than the position that I raised it initially. And that's due to the conservation of energy. And you will also deal with that in the upcoming chapters. But conservation of energy really says that the energy must be conserved in a system. What that means is, so if I gave it some potential energy, then all of that potential energy has to be converted into other forms of energy. It could be the kinetic energy, it could be, then there could be some very tiny amount of energies, there could be some heat energy, thermal energy, sound energy, and all of that, right? But the main thing, those are very negligible. You can consider them to be negligible. So you say that all the potential energy has to be converted into kinetic energy, right? Because I'm sure that you have heard of this very famous words that energy can neither be created nor it can be destroyed. So it has to convert from one form to another form. You cannot just get rid of energy. All right. So before we continue, let me just see how much time do we have left. Okay, we have almost 7 minutes, 6 to 7 minutes. Are we moving too slow?
No.
I think we're moving.
I think it's okay speed.
Okay, anyone else?
I think it's fine.
Okay, okay, if it's fine, then it's good. Everyone, can you all, because I keep forgetting, I'm sure you all have told me this before, but when are you guys appearing for these exams? October, November, or is it May, June?
I'm appearing in October, November.
You're okay, you're appearing in October, November. Okay.
Mhm.
And sorry?
Yeah, I am also appearing in October,
In October,
November.
November. All right, all right, all right. Okay. So, okay, I think it's okay. Let's we'll continue with this speed. If you want me to speed up, we can. I'll speed up as well. It's according to you, right? Anyways, so this is the situation. Now, one oscillation is basically when, if you look at this diagram, which is already drawn over here, if you release this bob from R, it goes to point Q, which is the mean position, and then it again raises to a height P. Now, this is half a oscillation. It has to come back to its initial position from which we released it. That would make one complete oscillation. Right? So is the idea of oscillation understood? So it's something like this. So if I release it from R, it will go to Q, then it will go to P, right? And then it will come back to Q and raise back to R. So this thing means one complete oscillation. So is that clear? The idea of an oscillation.
Yes, very much clear.
All right. Okay. So if it keeps doing so if it does the same pattern once again, as you can see, it starts from R, it comes back to R, and then it goes back to Q, P, Q, and then it comes back to R. So 2 times. So that's 2 oscillations. Right? Okay. So that's the idea of oscillation. Now there is something that is called time, or the period, or the time period. Now that is defined as, so this motion happened, how much time that it took for this motion to complete is the time period. And the time period, it's known as the time period. Time period is defined for an oscillation. So it means the time it takes to complete one oscillation. Complete one oscillation. So you have to be careful to what are you calling one oscillation. So the time it would take from it to start its journey from R, go to Q, P, and then come back to Q and back to R. So the time that it takes to do this thing is the time period of this oscillation. So is that clear?
Yeah.
All right. Now, the next term is known as amplitude. And amplitude is simply the maximum distance that this bob or ball will oscillate to, or you can say it is the maximum, or it is the distance between this resting position of this ball to any extreme position. It could be either R or P. Do you, if I say this, would you agree with me that the distance from P to Q is same as distance from R to Q? Would you agree with that?
Yes.
Does that make, okay, is that clear for everyone?
Yes.
Yes.
That does make sense.
Right. So it's basically coming from the conservation of energy. If I raised it to some height, I basically gave it some potential energy. Now, now this is also, you can say it's more or less of an ideal case, but it works. that there is no other force, no very negligible amount of air resistance. So you can say that the wind is very, the effects of wind are very small and all of that, right? So if that's the case, then it will not get, this potential energy would not increase. Nothing can increase this potential energy. You gave it some potential energy and you released it from there. Now all that potential energy has to be converted to kinetic energy, and then that kinetic energy would be maximum at this point Q, and then that would start again converting to the potential energy. So the total amount of energy is the same, and that energy keeps being distributed to potential, kinetic, potential, kinetic, potential, kinetic. But now you might also ask that in reality, when I practically perform this experiment, the bob eventually comes to rest. Why is that? Because according to what I just said, it should never stop, right? But it comes to rest. Anyone can tell me why is that so?
In theory, it's because it's corresponding to kinetic energy and potential energy, but there are other forces in reality.
Right. So is right. So we can include those forces in on paper as well. But yeah,